Okay, today we're going to talk about simplifying non-perfect radicals. So in your master copy, digital notebook, we're going to be starting on slide 78. That looks like this. And proceeding down to slide 82, which looks like this. But first, we're going to take our notes in our spiral notebook. So go to your TOC, it's table of contents, and we have simplifying non-perfect radicals. I'm on page 16 in my notes. You might be on a different page. Go ahead and mark that in. Again, it's simplifying non-perfect radicals. Page 16, it's going to cover slides 78 through 82. You may have to reorder some of your slides to make sure that that's happening. Give you a minute to get that copy down. Okay, so once you have that copy down, go ahead and go to your notebook page. Again, page 16. I'm going to copy it on a straight sheet of paper just to make it a little bit neater. So I'm on page 16 and simplifying radicals that are not perfect numbers. So the other day we talked about perfect square numbers and perfect cube numbers. In these situations, an example would be like 36 because 6 times 6 gives you 36, and it's called square because a square with a side of 6. 6 times 6 gives us an area of 36. Cube numbers are in similar fashion, except that they're a three-dimensional shape, so they would have two sides and a height. And if it's a cube, they're all squared or squares. And so if we had 6 times 6 times 6, that would give us our answer to that. So say if we had a cube that was an area of 125, we would know that the sides and the height are all 5 because they have to be the same. And roots go on and on. They go beyond 3. They go 4, 5, 6, really up to infinity. But what happens when that, if we factor it, we do the prime factorization, we don't have the same exact factors. So that's what we're going to be talking about today. So we're going to be drawing, let's go ahead, we're going to draw, say, step or rule. Give ourselves a lot of room to put that in. Do 2 columns here. Okay, so the first step or rule, so we'll call it ST number 1, is to find the prime factorization of the radicand. And you should remember that the radicand is what is underneath your radical sign. Prime factorization is breaking that down so that we have all primes, and that when we find the product of those prime numbers, it gives us the value of the radicand. So step 2, I'm going to say based on the index number. Remember, the index number is the little number that's kind of like inside the check. If we don't see one, we assume it to be 2. Remove one factor for each set. If no set exists, the radicand stays the same. Okay, step 3, multiply outside factors together and multiply inside factors back together. So one of the reasons that these are going to be imperfect is that there's no way that we can break this down into prime factorization that all the numbers are going to go into a set. And so we're going to have some factors left inside the radicand or inside the radical as the radicand, and we're going to have some outside, possibly. And so what happens is once we figure that out, we want to multiply the ones outside back together, and we multiply the ones inside together so that we have one number on the outside and one number on the inside. We don't want it to look like a string of prime factorization anymore. We're putting it back together. So then let's move on to step 4. We're going to put a little asterisk there. Sometimes this is needed, just like sometimes this may not be needed. So step 4 is going to be talking about the variables. Like what happens if you have a number and it has variables attached to it. So for variables, divide the exponent by the index number. The answer is the exponent for the outside factor. The remainder is the exponent for the inside factor. So in other words, like if there are variables involved, we're not going to necessarily prime factor the variables. And the reason for that is because they already are, right? So if you have x cubed, that's x times x times x. We're not going to find a different factor. It's not going to be y if we have x's. So in essence, it's already in its prime factorization state. So then rather than write it out in expanded form, which you could do if you want to, we're just going to take its exponent, and divide it by the index number to see how many sets we have that would need to come out. And if there's a remainder, that is going to be how many of that factor need to remain inside. So then the last thing, of course, should be our answer. Okay, so let's go ahead and do an example. Hopefully, yeah, you guys are able to see all that. So say we have the square root of 72. Okay, well, the first thing I want to do is find its prime factorization. I'm going to use upside down birthday cake for that. So I have 72. It's divisible by 2. It's going to be 36. That's divisible 18, 2, 9, 3, 3, 3, and 1. Okay. This is, as I said, the birthday cake method. So then what I want to do is I want to look and see, based on what I found out, based on the index number, do I have any sets? So let's see, starting at the top, I have a set of 2 and I have a set of 3, right? And those are sets because we're looking for a square root. Square is 2. It's telling me I need 2 identical factors in order to make a set. So then what am I going to do with them? Well, I'm going to move those outside. 2 comes out and 3 comes out, right? So 2 2s don't come out, 2 3s don't come out, 1 come out. That set creates one of the factors outside the variable. Set one of the factors outside the variable. And left inside is the set that we didn't circle, and that's the 2. Right here, put a little box around there. And then we multiply our outside factors. 2 times 3 is 6. We only have one inside factor, so it remains the same. We don't have any variables, and so our answer is 6 radical 2. And just to check my work, let me write check here. Basically, because this is a square root, that would be like saying is 6 to the second power times 2 equal to our original number of 76 or 72. So 6 times 2 is 36. 36 times 2 is 72. And I say yes, so this is correct. Okay. Now, one interesting thing that you may have noticed is if you knew that 36 was a perfect number right here, you could have approached this in what's known as the perfect number method. And so we could say 72, and we know 72 can be broken down in a perfect number of 36 and 2. And from there, I would look at it as the square root of 36 to 36 would create a 6 outside, which is what I wound up with, and 2 was left inside. But that's just another way to approach it. And as you get more familiar with the perfect numbers and the square number, or perfect squares and perfect cubes, that might become a little bit easier. But sometimes when you have really large numbers, it's hard to see those perfect square numbers inside of the number that you're trying to simplify that's not perfect in and of itself. So let's look at another one here. What would happen if we added variables to this? Well, let's look at the square root of 72, a to the 7th power. Okay, so we already know that the birthday cake for 72, at least we should, right? We're going to have a 2, 36, 2, 18, 2, 9, 3, 3, and 3, 1. We know that we have a set of 2s, and we have a set of 3s, and this 2 stays inside. Okay. So coming down here, we'd still have 2 times 3 radical 2, and then I still have a to the 7th. I haven't done anything with that yet. Outside 6, radical 2a to the 7th. And now I have to do the part with the variables. So the exponent for a is 7. My index number is 2. 2 goes into 7 3 times, giving me a 6, and I have a remainder of 1. So according to this, what's going to happen is, 6 is still outside. Then I'm going to have my a, and according to the rule, it says that divide the exponent by the index number. The answer is the exponent for the outside factor. So that's saying a is going to be an outside factor 3 times. And the remainder is the factor for the inside. So I still have that 2. And now I have a, and my remainder is 1, so it's 1. I don't need to put a 1 there. And that is a simplification of 72a to the 7th, right? Let's look at what happens, it mentioned up top here. If no set exists, the radicand stays the same. Let's think of a number where there's not going to be any matching factors. I can think of 33, right? 33 isn't a prime number. It is, in fact, divisible by 3 11 times. But when I look here, the prime factorization is 3 times 11. There's not a set there to make that happen. So in that case, the square root of 33 is simplified. That's as low as we can go. We can't go any further because it doesn't have any identical sets to satisfy the square root. What would happen if we're looking for the cubed root of something? So say we're looking for the cubed root of, so 3 is going to be my index number, of 32. Well, I'm still going to start and do my tree. 2 goes into 32 16 times. 2 goes into 16 8 times. 2 goes into 8 4 times. And 2 goes into 4 2 times. 2 and 1. So my birthday cake is going to look something like that. Starting at the top, I need to circle sets of 3 this time. So I have 1 set of 3 and 2 2s that don't come out. So according to this, on the outside, I'm going to have a 2. I'm still going to have my cubed root radical. That doesn't change. And inside, I have 2 times 2 still. So according to my rule, I multiply the inside back together. So I have 2 radical 4. Okay, so important things. This 3 needs to be in your answer, right? The index number doesn't change. That needs to be with it. That doesn't leave the radical. You can't change it all of a sudden to a square or to a fourth. It doesn't get multiplied by anything. It's simply a characteristic of the problem. It's telling you what you're looking for. Okay, there's no way to change that in the problem. It's going to stay a cubed root. So that's one of the differences. A perfect cube number, we know 8 is a perfect cube number because 2 to the 3rd power, right, meets that. So once you know that, you can also look and do the same thing you did with the variables. 3 divided by 3 is 1. So 2 to the 1st comes out, there's no remainder, and my answer would just be 2. That's another way to approach it as well. Okay, so today you're going to have to go back and we have a lot of practice. Now, I didn't put the upside down birthday cakes in there for you because that's something I expect you to do in your notebook or on paper. And when I say on paper, I don't mean scratch paper. I mean be organized in your work. Okay, some of the slides you're going to have to do. This slide tells you for each expression, drag and drop either yes, if it needs to be simplified, or no, if it cannot be simplified. So if it's a number like we had 33 on our notes, that's a no. If it's a number like 72, that's a yes. So you need to go through these and answer yes or no first. Then it says, for each expression marked yes, drag and drop the correct equivalent expression onto the second circle. Okay, so that's what you're going to do. You're going to, not all of them are going to have an answer because not all of them are going to be yes, and not all of the answers will be used on that slide. And that is radicals.